We introduced the Biot Savart Law in last lecture. Now let me give you some examples to show how to calculate the magnetic field by applying this law. Consider a thin straight wire of a finite length carrying a steady current I. It's placed along the x-axis as shown in the figure. Please determine the magnitude and direction of the magnetic field at a point P due to this current. This is a typical example of an application of the Biot Savart law. Let's consider a length element ds located a distance r from the point P. Firstly, we examine the direction of the magnetic field dB at P due to the current element IDS by the right-hand rule. It's out of the page because the cross product is out of the page. Actually, because all the current elements are located in the plane of the page, they all produce a magnetic field out of the page at the point P. Therefore, the direction of the total magnetic field B at P is out of the page, and we need only consider the magnitude of the field. Please see this triangle. We find the cross product of ds and r roof. ds cross r equals dx cosine theta k roof. K roof is a unit vector which is out of the page. By using the Biot Savart law, we write this expression for dB by replacing the cross product. From the geometry, we express r in terms of theta. R equals a divided by cosine theta, and x equals minus a tangent theta. We find the differential dx as expressed by this one. Now substitute dx and r by the expressions in terms of theta. Integrate dB over all length elements making up the wire, where the subtending angles range from theta 1 to theta 2 as defined in the figure. This is a magnetic field due to a finite straight wire carrying a current I. Now, I have a question. If the wire becomes infinitely long, how about the magnetic field? In this case, we know theta 1 equals 19 degrees and theta 2 equals minus 19 degrees. Then the field becomes this one. B equals mu0 times I divided by 2 pi a. These two equations show that the magnitude of the magnetic field is proportional to the current I and decreases with increasing the distance a from the wire. Please recall the electric field due to an infinitely long line with the linear charge density lambda. E equals lambda divided by 2 pi epsilon 0 r, which has a similar mathematic form as the one for the magnetic field due to an infinitely long wire. Okay, let's examine the features of the field produced by a wire of an infinite length. From this expression, we can see that B has the same value for all points distance A from the wire. Correspondingly, the system has a cylindrical symmetry, and the magnetic field lines are circular as shown in this figure. The magnetic field lines are circles concentric with the wire, so the magnitude of the field is constant on any circle of radius A. The field lines are in planes perpendicular to the wire. Then how about the direction? We could determine the direction by applying the right-hand rule as shown in the figure. If my right thumb points along the direction of the current in the wire, then the 4 fingers of my right hand curl in the direction of the magnetic field. Let's discuss the next one. Please look at this figure. We wish to find the magnetic field at a point O for the current carrying wire segment. We notice The wire consists of two straight portions and a circular arc of radius a, which subtends an angle theta. Obviously, the magnetic field at O due to the current in the straight segments is zero because the length element ds is parallel to R roof, causing the cross product to be zero for these paths. Therefore, the magnetic field at O is only due to the current in the curved arc of the wire. Now we apply the Biot Savart law to evaluate the field at O due to the circular arc of the wire. We notice that the element ds along the path AC has the same distance a from O, and the vector ds is perpendicular to R roof at every point along the path AC. Therefore, the magnitude of ds cross R roof equals to ds. We could determine the direction of B by applying the right-hand rule. Each current element produces dB, which is directed into the page at O. Based on this analysis, the magnitude of the field dB at O due to the current in the element of length ds could be expressed by this one. Integrate dB over the curved path AC, where A and I are constant and they can be removed from the integral sign. The line integral of ds is S, which is A times theta. So we have this expression for the field B. Well, please look at this expression. I have a question here. Based on this result, could we find the magnetic field at the center of circular loop of radius r that carries a current I? We notice that the curved segment becomes a full circle when the angle theta increases to 2 pi. The magnetic field at the center of the wire loop can be determined when theta equals to 2 pi. So it equals mu0 times I divided by 2a. Okay, now please consider a circular loop of radius a in the YZ plane. It carries a steady current I. We wish to find the magnetic field at a point P on the x-axis, a distance x from the center of the loop, as shown in the figure. Let's firstly check the field contribution dB at P due to a single current element ds at the top of the ring. The field dB can be resolved into two components, dBx parallel to the axis of the ring and dB vertical perpendicular to the axis. Noting that the symmetry of the situation, we are interested in the magnetic field contribution due to a current element at the bottom of the loop. We found that the perpendicular components of the field due to the current elements at the top and bottom of the ring cancel. Obviously, the perpendicular components of the field contributions due to each pair of the current elements cancel. Hence, the resulting magnetic field has only component dBx, and we only focus on the parallel components and obtain the total field by summing them simply. We write the expression for dB by applying the Biot Savart law. From the geometry shown in the figure, we notice that each length element ds around the loop is always perpendicular to the vector r at the location of the element. So, the magnitude of ds cross r equals to ds, and all elements around the loop are at the same distance r from P. We substitute r squared by this one, a squared plus x squared. The x component dBx equals dB times cosine theta. Integrate dBx over the entire loop. We find cosine theta from geometry shown in the figure and substitute cosine theta by this expression. A and x are both constants, and we remove this part from the integral sign. Integrate ds over the loop and find the field finally. Based on this result, we could also find the magnetic field at the center of the loop when we let x be 0. Bx equals mu0 times I divided by 2a. This is exactly the same result as the one from the circular arc. Now, let's look at the figure showing the pattern of the magnetic field lines for a circular current loop. Obviously, it's similar to the pattern of the field lines around a bar magnet, both of which has axially symmetric. Then how to determine the direction of the magnetic field? Right-hand rule. If your four fingers direct along the current, your thumb points in the direction of the field. We have seen that a current-carrying wire produces a magnetic field. Also, we know a wire carrying a current will experience a net force exerted by a magnetic field. Then, if there are two current-carrying wires in space, what happens? We expect two current-carrying wires to exert a force on each other. Let's consider an easy case. Please look at this figure. There are two parallel wires separated by a distance a and carrying currents I1 and I2 in the same direction. Here we treat the wire 2 as a source wire carrying the current I2 and wire 1 as a test wire carrying the current I1. Firstly, we could compute the magnetic field B2 created by the current I2. We know that the magnetic field lines due to I2 are circles concentric with wire 2, and B2 is tangent to the circle at each point. Since the wire 1 is parallel to the wire 2, at each point on the wire 1, B2 has the same direction and the same value. It's perpendicular to the wire 1 as shown in the figure. We use F1 to denote the force on the wire 1 exerted by B2. F1 equals I1 L cross B2. Because L is perpendicular to B2, we have this one. F1 equals I1 times L times B2. B2 equals mu0 times I2 divided by 2 pi a. We substitute B2 by this expression and obtain the force on wire 1. We could determine the direction of F1 by the right-hand rule. F1 is directed toward the wire 2 as shown in the figure. We could follow the same operation to calculate the force F2 on the wire 2 exerted by B1. F2 is equal in magnitude and opposite in direction to F1, which is consistent with Newton's third law. In this case, the two wires attract each other. When the direction of one current is reversed, in other words, the currents in these two wires are in the opposite directions, the forces are reversed and the two wires repair each other. We could draw a conclusion here. Two parallel wires carrying currents in the same direction will attract each other. On the other hand, if the currents are in opposite directions, the two wires will repair each other. Well, in the next lecture, we'll further explore the features of the magnetic fields produced by the current distributions with symmetries, and we will find an important law in magnetism.